The following content is supported by victoris.org.
The last example we'll consider is the maxsum. The maxsum question goes as follows. Suppose we have an array A. We're going to find the subarray with the greatest sum. In this case, a subarray means a contiguous selection of elements in this array. If our array A is given as follows, then one can check that the maxsum is 3, which is given by 2 plus minus 1 plus 2. One can try to do a brute force approach by considering all ranges S to E. The naive way will be using 3 for loops, right? The first one for all the starting indices S, the second one for all the ending indices E, and the last one to go from S to E, sum up all the array elements. This has 3 for loops, each one incurring a worst case time complexity of On, and so the total time complexity is On cubed. This is a bad time complexity, and even with prefix sum, which we learned in the previous lesson, it will still be On squared. We can do better, and the Kadane's algorithm would show us how to do it with On time. Now, here's how the Kadane's algorithm works. The idea is that if we want to look through every single subarray from S to E, the current approach we're taking is to look through all the starting S values, then we look through all the E values, fixing S. In other words, we have a for loop for E enclosed within a for loop for S. Both of these cost On time. However, one can actually have the E for loop outside the S for loop, and then we look through all the values of S, fixing the index E. Now this might seem like a very small change because both of them are still On time, but the key observation is that we can actually save time by using dynamic programming to change this On into O1. And how do you do that? We consider the function maxsum of x to be equals to the maximum contiguous sum starting from any index I less than x and ending at index x. This is similar to the longest increasing subsequence. If this definition is confusing, it simply means that maxsum of x is calculated as follows. We find the best starting point I among all possible starting points for a given fixed ending point x. This x over here is basically the E that we're fixing. Now, if we write out the definition of the maxsum of x as follows, specifically maxsum of x is equals to the maximum among all these subarray sums, starting from index 0 to index x, index 1 to index x, and so on until x alone. You can see that this triangle has a repeating substructure. Specifically, this green box over here has actually been calculated before when we calculated maxsum of x minus 1. So, maxsum of x is actually calculated as maxsum of x minus 1 plus ax or ax alone. Now, this has saved a lot of time because in the previous calculation, we need to look through On possible candidates for the maxsum of x. However, now we only need to look through 2 possible candidates for maxsum of x, provided we have calculated maxsum of x minus 1 first. And this, if we look carefully, is just a recursive definition for maxsum of x. And that is how we use dynamic programming to speed up computation. We observe a repeating substructure, which is this triangle over here, and we realize that we do not need to recompute it if we have calculated it before. Base case would be maxsum of 0 is equals to a of 0. The transition going from the state I minus 1 to the state I will be as follows. Let's run the following algorithm on the example array over here. We see that maxsum of the first index is simply a of 0, which is 8, because that's the base case. The maxsum of the second index is either maxsum of I minus 1, which is 8 plus a of I, or a of I alone. In this case, we're considering between 8 plus 9 and 9 alone, and we see that 8 plus 9 is clearly better, so the maxsum is 17.